This is going to be a very short lecture on Greens Theorem, named after someone's name there, someone named Green. The idea behind Greens Theorem is that we can do line integrals a little bit easier, often by using the fact that if the curve is a closed curve, that means that it comes back to itself. So your initial point on the curve is the same as your terminal point on that curve. Then you can often convert this into a double integral over the region it encloses. So more explicitly, the theorem looks like this. And we'll see some examples on how this works. But first, let me clarify a little bit. There's a lot of words here. This is basically meaning that, again, the curve is starting at some point and then it ends up back where it starts. The curve doesn't cross over itself. It's in the finite plane and it's piecewise smooth, which means that if you define it in terms of, say, x of t and y of t, that these functions are differentiable except for at finitely many points. So there might be finitely many points where the derivative does not exist, but otherwise you can take the derivative other places. So that's what all those words mean. There is also an oriented counterclockwise part of this theorem. And what that means is that as t increases, you want to be going around this curve, this region you're describing by this curve, in a counterclockwise direction. What happens if it's going clockwise is that you have to put a minus sign in front of this then. So you just get the negative of this if it's going clockwise. But for going counterclockwise, this is what this theorem gives you. So let's just do some examples here. So this first one is a line integral, and this little circle just means that it's coming back to itself. But we have this line integral, and we want to go around this circle with center at the origin and radius 2. So it doesn't give us what the parametric equations are. You don't need those parametric equations necessarily for Green's theorem, but if we're going to compute this directly, we want to know what those parametric equations are. So by directly, this means we want to do it the way we learned in the last lecture. So let's check. If I wanted to describe the circle with radius 2 centered at the origin, that's similar to what we do with the unit circle, but the radius 2 puts an extra 2 here. So x equals twice cosine theta, y equals twice sine theta. Theta goes from 0 to 2 pi, gives me the whole circle. So when theta equals 0, we're at x equals 2 and y equals 0, so we're at 2, 0. And then when theta equals pi halves, this will be 0 and this will be 2. So we'll have x, y being the point 0, 2, and so we're at 2 on the y-axis. And as theta increases, you're going around the circle counterclockwise. So I use theta here instead of t like we were doing before, just in part to emphasize that it doesn't have to be t for your variable. But we want to rewrite this line integral in terms of theta. We want everything in terms of theta. We got x and y in terms of theta. Now we need dx and dy. Well, you can see what dx and dy are. And I could probably just write this down. The integral is going to be 2 cosine of theta for the x here minus 2 sine theta for the y. So this is x minus y. 2 cosine of theta minus 2 sine theta. And then I want to multiply that by dx. Dx is going to be minus 2 sine theta d theta. So dx is minus 2 sine theta d theta. Then we want plus x plus y. X plus y is again 2 cosine of theta plus 2 sine theta for those. So then we get dy, and dy is going to be twice cosine of theta d theta. So that's what's written here. And we want theta to go from 0 to 2 pi. So this is how we would evaluate this directly, this line integral. So this simplifies. We have a minus 4 sine theta cosine theta and a plus 4 sine theta cosine theta. Those are going to cancel each other. And what's left is a 4 sine squared theta and a 4 cosine squared theta. So 4 sine squared theta plus 4 cosine squared theta. You can take the 4 out of that, and you just have sine squared plus cosine squared theta, and that's 1. So this is just going to be 4 times 1, or 4. So when we simplify that, we just have the integral of 4 d theta from 0 to 2 pi. That's 4 theta evaluated from 0 to 2 pi is just 8 pi. So that gives me the value of this line integral computed directly, and it's 8 pi. And we want to do it now with Greens theorem. Of course, we should end up with the same answer, 8 pi. So let's see what Greens theorem does for us. This wasn't too bad. I noticed that the only hard part was perhaps even just getting the parametric equations. But after that, it was fairly direct what we had to do. And this should not have been too bad either. To remind you what Greens theorem is, I put that there. And now we want to do B. We can rewrite this as a double integral over the region that's enclosed by the curve, which is the circle of radius 2 centered at the origin here. So let me go ahead and just call that R. That's the circle of radius 2 centered at the origin. And we have dA here. We want to calculate whatever this is here. And to clarify, g is the function in front of the dy here, so we want to take the derivative of this function with respect to x. So that's giving me 1. Then we want to subtract. We take the other function that's in front of the dx here, this one, and take the derivative with respect to y. So we take the derivative with respect to y and get minus 1. So I have the derivative of the function with respect that's in front of the dy with respect to x is 1. And subtracting the function that's in front of the dx here, its derivative with respect to y, and that's the minus 1. So this is just going to be 2. 1 minus the negative 1. So I'm just getting twice the double integral dA, and this is just the area. You integrate 1, you're just getting the area of the region R you're integrating over, which was a circle of radius 2 centered at the origin. So we're just getting 2 times pi r squared, where r is 2, pi times 2 squared. And so that's just giving me 8 pi. And so that gave us 8 pi then for the answer to this line integral by using Greens theorem. You can see the process is quite a bit different than what we just did for part A, but we did get the same answer, 8 pi. And that's what Greens theorem allows us to do, is this process. So let's look at this problem. Here we have a rectangle. Let me draw a picture of this rectangle. So the curve is going from the origin to 3, 0, to 3, 1, and then to 0, 1, and then back. So that's the region described by this curve. It's enclosing this rectangle here. We're not going to do A here. I'm more interested in Greens theorem for this lecture, but A would be a little bit difficult because we'd have to break up the curve into 4 different parts. So each of these parts of each of these sides of this rectangle. And those parts, we'd have to calculate this integral over those parts separately and then add them together. So that's a little messy. Greens theorem will allow us to do this with just one double integral. So the double integral is over this rectangle enclosed here. And let's see where I got this information from. We want to take the derivative of what's in front of the dy again, the g here, with respect to x. So that's going to give me 2x. And then I want to subtract what's in front of the dx, that's the f here, and I want to take the derivative of that with respect to y, which is giving me the x. So the derivative of what's in front of the dy with respect to x is giving me the 2x, and then I'm subtracting the derivative of what's in front of the dx with respect to y. So it's giving me 2x minus x, which is just x. Now I want to calculate that. It's not an area anymore because of this x being here. But we're just over a rectangle, and in this rectangle, we can see that y goes from 0 to 1, and x goes from 0 to 3. So if I set this up as a double integral over r, that just means I want to take y from 0 to 1 and x from 0 to 3. These can be any order because this is a rectangle. It won't change what the limits are if I change the order. It'll just change the order of the integrals here and the d's here. But this is what I'm integrating. X for this, and dx dy, y is going from 0 to 1, x is going from 0 to 3. Integrating with respect to x first, I'm going to have x squared over 2, evaluate from x equals 0 to 3. That's going to give me 9 halves. And I'm just left with integrating 1 dy, which is going to give me a y, evaluate from 0 to 1 will give me 1. So this is just 1, and so I end up with 9 halves. So the answer to this problem is 9 halves. Let's go ahead and look at Greens theorem for calculating this line integral. It looks a little messy. Let's go to it. So what's the region we're integrating over? We have a line segment going from minus 2, 0 to 2, 0 on the x-axis. And then we want to go from 2, 0 back to minus 2, 0 along the circle x squared plus y squared equals 4 above the x-axis. So it's a half circle like we had before, but we're starting at minus 2, 0, going to 2, 0, and then doing a half circle on top. Notice that's counterclockwise. So that's the region we'll be integrating over, that half circle. And where did this come from? Well, Green's theorem, let's see if we can remember now. We take what's in front of the dy here, take the derivative with respect to x. That's going to be 3 minus e to the x minus 2x times sine of y. 3 minus e to the x minus 2x sine y. So that's the derivative of this with respect to x. And then we want to subtract the derivative of what's in front of the dx here. Subtract the derivative of this with respect to y. We're going to get a 1 minus e to the x. Derivative with respect to y will be minus sine y times a 2x. Okay, so we have 1 minus e to the x minus 2x sine y. So that's what's inside the integrand of this double integral. And let's go ahead and look at what that gives us. The minus e to the x will cancel because we have minus e to the x minus a minus e to the x. The minus 2x sine y will cancel because we're subtracting minus 2x sine y as well. So those cancel. I'm left with 3 minus 1. So this whole thing is just 2 when I simplify. Again, this is the area of R. R was this half circle centered at the origin of radius 2. So we want to do half the area of a circle of radius 2. So I have the 2 initially. I have the half for part of the area here times pi r squared, where r is 2. So this will cancel. I'll just have 4 times pi for my answer. So the answer to this line integral, the value of it is 4 pi. And I'm going to end the lecture there with that example.